This is M.W. Penn. At conferences of the National Council of Teachers of Mathematics, I often present sessions modeling operations with fractions. I find that most of the complicated operations involve the division of fractions, so I've decided to split that up into several different pieces. In this session, I would just like to talk about the division of a fraction by a whole number. And the slides of the presentation are courtesy of MathWord Press. Dividing fractions by whole numbers. What types of problems are these? Well, suppose we had half a pizza and there were 3 of us. We'd have to divide that half pizza into 3 equal parts. But what part of the whole pizza would we each eat? Or suppose I had 1/3 of a gallon of milk and 5 kittens to feed. I would have to divide that 1/3 of a gallon into 5 equal parts. You may have learned an algorithm to perform this operation. An algorithm is a formula to solve a problem. In this case, the algorithm says that you should multiply the fraction by the reciprocal of the whole number. In the example here, we have 1/2 divided by 3. Following the algorithm, we would multiply 1/2 by the reciprocal of 3, or 1/3, and the answer would be 1/6. So 1/2 divided by 3 equals 1/6. This formula uses a reciprocal. But do you know what a reciprocal is? It's a rather big word for a rather simple concept. A reciprocal is a number related to another number in a way that their product always equals 1. That is, when you multiply them together, the answer is always 1. We also call this the multiplicative inverse. Another big term, but the concept remains the same. For example, the reciprocal of 3 equals 1/3, because when you multiply 3 times 1/3, the product is 3/3, which, of course, equals 1. The reciprocal of 1/7 would be 7, because 7 times 1/7 would equal 1. How about 3/4? What would the reciprocal of 3/4 be? Well, it would be 4/3, because when you multiply 3/4 times 4/3, the product is 12/12, which of course equals 1. In fact, the reciprocal of any fraction, a over b, is another fraction, b over a, because when you multiply them together, the product is always 1. Why do we use this algorithm to perform this operation? Never ask the reason why, just invert and multiply. I think we can do better than that. When we memorize an algorithm, a formula to solve a problem, we have to always remember 2 things: what the formula is and when we're supposed to use it. Instead, let's look at what we're doing. Perhaps we can figure out the solution ourselves. So what are we doing here? We're dividing a part of a whole into equivalent smaller parts. Suppose we had half a cake. If we wanted to share 1/2 of a cake equally among 2 people, what fraction of the whole cake would each person receive? Bear might say, I only have half the cake. Now I have to share it with you. That means I won't have much left. And he's right. A fraction of a portion is a smaller number. At the bottom of this slide, we have a model of a cake, an area model, and we can see that the entire cake has been divided into two equal portions, or halves. And one of these halves has been divided by 2. If we divide 1/2 into 2 equal portions, we can see that each of those portions would be equal to 1/4 of the entire cake. Below the area model, we have a number line model. This number line model shows a unit, 1, divided into 2 equal parts, or halves, and one of those 1/2s divided by 2, divided into 2 equal parts, or 1/4. Do you remember the parts of a fraction? You can see that a fraction is written with a number on the bottom, the denominator, and a number at the top, a numerator. The denominator tells us how many equal parts divide a unit, and the numerator tells us how many of these equal parts we have. Here on the number line, we can see a unit divided into 3 equal parts, or thirds, and 4 equal parts, or fourths. The denominators, the 3 or the 4, tell us how many equal parts there are in a unit. But that number on top, the numerator, tells us how many we have. On the number line here, we can see 1/3, 2/3, and 3/3. And we can also see 1/4, 2/4, and 3/4. Because the denominator tells us how many equal parts divide a unit, we can see that as the denominator increases, we have more and more equal parts in the unit. But as the denominator increases, these parts become smaller. Here we see 1/3, a 1/6, and a 1/9. More and more smaller parts. When we add fractions that share the same denominator, or when we multiply fractions by a whole number, we're just counting up how many of the same size parts we have. Let's look at these fourths in an area model. We can have 1/4, 2/4, 3/4, 4/4, 5/4, or more. What we're counting up is fourths. As the denominator remains the same and only the numerator increases, we have more and more of the same size parts. Adding fractions with the same denominator is just a matter of counting up how many we have. How many what? How many equal parts. Here we see an area model of fourths. If we have 1/4 and add 2/4 more, we have 3/4, 3 of the same size equal parts. 2/3 plus 5/3, we have 7/3. 4/5 plus 2/5, we have 6/5. We're adding thirds, or fifths, or fourths. When we multiply a fraction by a whole number, we're actually doing repeated addition. Think about that. We're just counting up the number of equal parts that we have. If we have 1/2 and we're multiplying it by 4, Bear might say that we have 1/2 and 1/2 and 1/2 and 1/2. We have 1/2 4 times. We have 4 halves. If we have 3/8 and we multiply it by 2, well, we have 3/8, and then another 3/8. We have 6/8. 2/3 times 5 means that we have 10 of those equal parts. We have 10/3. Multiplying a fraction by a whole number is a simple computation. So when we multiply a fraction by a whole number, we only multiply the numerator of the fraction by the whole number to find out how many we have. 1/3 times 5 means that we have 5/3. 4/4 times 2, we have 8/4. 3/5 times 6, we have 24/5. Now, when you think about it, it only makes sense that when we divide a fraction by a whole number, we should only divide the numerator of the fraction by the whole number to find out how many we have. 5/3 divided by 5 should equal 1/3. 8/4 divided by 2 should equal 4/4. 24/5 divided by 6 should equal 3/5. When we multiply a fraction by a whole number, we now understand why we really only multiply the numerator of the fraction by the whole number. So when we divide a fraction by a whole number, it makes sense that we only divide the numerator by the whole number. Let's look at this example of 2/3 times 7, which gives us the product of 14/3. If we were to divide 14/3 by 7, if we divided 14 by 7, it would give us the answer 2/3. So essentially, that's what we want to do. We want to divide the numerator of the fraction by the whole number. But what happens when we multiply the fraction by the reciprocal of the whole number? That has the effect of making the denominator of the fraction larger. And think about that. What happens when the denominator becomes larger? It makes the parts of the whole smaller. So if we have the fraction 14/3 and multiply it by the reciprocal of 7, which is 1/7, the product is 14/21. We have, in essence, increased the denominator. And when we look at 14/21, we realize that it does equal 2/3. So the formula works. But let's look at that again. So when we multiply a fraction by a whole number, we really only multiply the numerator by the whole number. Here we're looking at an area model for 1/6. When we multiply 1/6 of a unit by 2, the product is 2/6. Or, as we can see in the area model, 2/6 is equal to 1/3. If we were to divide 1/3 by 2, we realize that our answer should be 1/6. But if we multiply 1/3 by the reciprocal of 2, which is 1/2, the product is 1/6. We have actually increased the number of parts dividing the unit. Instead of a unit divided into 3 equal parts, we now have the unit divided into 6 equal parts, and we have one of them. Let's look at another example. Here we have a unit divided into 9 equal parts, or ninths, and the numerator tells us that we have 4 of them. We have 4 ninths. If we were to multiply 4 ninths times 2, we would really only multiply the numerator, the 4, times 2. And that would give us a product of 8 ninths. Yeah, that makes a lot of sense. Okay, so now we have 8 ninths. Suppose we wanted to divide 8 ninths by 2. In essence, we're reversing the multiplication we just did. We're dividing 8 ninths by 2. 8 ninths divided by 2 equals 4 ninths. If we divided only the numerator by 2, it would give us that answer. But what if we multiplied 8 ninths by the reciprocal of 2, 1/2? The product of 8 ninths times 1/2 is 8 eighteenths. But look at these area models. 8 eighteenths is equivalent to 4 ninths. So when we follow the algorithm, we're essentially performing the same operation as dividing the numerator of the fraction by the whole number. Let's look at another example using the algorithm. Here with one of Bear's famous cakes. We have an entire cake divided into 1/8 pieces, and we have 5 of them. So we have 5/8 of the cake, and we want to divide it by 2. When we follow the algorithm, we multiply 5/8 by the reciprocal of 2, or 1/2, and the result is 5 sixteenths. If we look at the area model, we can see 5/8 and 5 sixteenths. And we see that 5 sixteenths really is 1/2 of 5/8. By multiplying the denominator of 5/8, the 8th, by 2, we have essentially performed the division. Let's look at this computation one more time. We know that when we multiply a fraction by a whole number, we are only multiplying the numerator. We're increasing the number of equal parts that we have. And we realize that when we divide a fraction by a whole number, we should actually only divide the numerator. So why multiply the fraction by the reciprocal of the whole number when we can simply divide the numerator of the fraction by the whole number? Let's look at that computation one more time. We have 5/8 divided by 2. And in order to solve the problem, we've multiplied 5/8 by 1/2. And we found that our answer was 5 sixteenths. On the bottom, we can see the area model for an entire cake, 5/8 of the cake, 1/8 of the cake, and 1/16 of the cake. we see that when we multiplied 5/8 by 1/2, the answer was 5/16. I've circled them here at the bottom. But suppose we actually divided the 5, the numerator, by 2. Well, 5 divided by 2 is 2.5. So if we did that, our answer would be 2.5/8. But 2.5/8, well, count them up. 2.5/8 is equal to 5/16. 2.5/8, though, is a rather complicated number. 5/16 is much easier to work with. And since both computations yield the same answer, it's just easier to multiply 5/8 by the reciprocal of 2, which is 1/2. So in essence, the algorithm doesn't change the answer. It simply gives us an easier computation. Another example of this division. We have 2/3 of a chocolate bar and we want to share it equally among 4 friends. What fraction of the entire bar will each person receive? On the number line, we've divided a unit into thirds. We've taken 2 of those 1/3, and we've divided that 2/3 into 4 equal parts. At the bottom, we have an area model for the same problem. We have an entire bar, 2/3 of the bar, and the 2/3 of the bar divided into 4 equal parts. If we follow the algorithm, we have 2/3 divided by 4, which is equal to 2/3 times 1/4. The answer is 2/12 or 1/6. So when we divide a fraction by a whole number, we now know that the result will be an even smaller fraction. We will have a smaller portion of the whole, only a part of a part. And now we know why the algorithm works. In this slide, we're looking at a few examples of the types of problems we've just been studying. If you have a half yard of cloth used to make 2 aprons, it's 1/2 divided by 2. 2/3 of a gallon of milk divided between 3 cats, 2/3 divided by 3. 4/5 of a meter of string divided between 2 packages, 4/5 divided by 2. If Pooh Bear has 1/4 of a pot of honey and wants to give an equal part of it to 2 of his friends, he would have to divide that 1/4 of a pot of honey into 2 equal parts. 1/4 divided by 2 is equal to 1/8. This is M.W. Penn, and Sam and I hope that you'll enjoy math as much as we do.